Welcome to today's lecture. This is now the fifth lecture in the series and the second lecture of part 2 on post-training. So this is on turning language models into agentic systems. Today we're going to cover reinforcement learning for language models. So last lecture we talked about the idea of post-training, and we talked about the post-training pipeline, which is you begin with your pre-trained system, so you undergo generative pre-training. Then you take that system, you do supervised fine-tuning, and then reinforcement learning on it. Supervised fine-tuning is what we covered in the last lecture, so we discussed this in a lot of detail. Essentially what you do is you have a data set of prompts, and then you have human-written completions to those prompts, showing the kind of behavior you want the language model to exhibit. And then you train the language model to predict those completions given those prompts. And finally, we discussed fine-tuning attacks, and I introduced this idea that in general, fine-tuning the language model does not remove any of the internal mechanisms that are capable of generating the unwanted behaviors or capabilities. Instead, it sort of hides or suppresses these behaviors and these capabilities. Because it's only doing some superficial hiding of the behaviors and capabilities, you can recover these via what we call fine-tuning attacks. So let's just recap this pipeline that we covered in the last lecture, the post-training pipeline. So we begin with self-supervised learning by next token prediction over a large data set. And then from here, we go to supervised fine-tuning by next token prediction on expert demonstration, so written completions to these prompts. And this is what we covered last lecture. And then finally, we do reinforcement learning from human feedback. This first part is pre-training, and these second two parts are post-training or fine-tuning. This lecture and next lecture, we're going to cover reinforcement learning from human feedback. This lecture is on the reinforcement learning part. Next lecture is on the human feedback part. All right? Great. And to remind you of why we care about this, this is showing the win rate against the supervised fine-tuned 175 billion parameter model. So this is the GPT-3 model family. And the top two lines, so PPO and PPO pre-training mixture, these are the RL'd versions of the model, so the version of the model that's been both SFT'd and RL'd, and we can see that it wins pretty consistently, so about 60% of the time, against only the supervised fine-tuning model, which itself beats both GPT unprompted and GPT with in-context learning of the behavior that you want to exhibit. Great, let's get started. So what are we gonna cover today? What's going to be in today's lecture? Well, we're going to talk about the reinforcement learning objective. So we're going to write down what it is that you're trying to optimize when you do reinforcement learning. And then I'm going to cover a very simple reinforcement learning algorithm. Now, this algorithm is called reinforce. It's a very simple algorithm, and it's not used in practice. Some variations on it are, and the reason I'm introducing it here is because it's pretty easy to do the derivation of it. It's pretty simple to see how it works. There's nothing particularly complicated going on, but it gives you the key intuitions to understand a whole family of more complicated, more in-depth reinforcement learning methods. So we're going to cover this, and it's going to give you good intuition for if you want to go and read in more detail about how these other methods work. I'm then going to cover another method for kind of solving the reinforcement learning problem, which is called best-of-n sampling. And then after that, I'm going to provide a dictionary for converting between reinforcement learning on language models and reinforcement learning in more standard settings. So you may well have taken a course in reinforcement learning before, or at the very least encountered some of these ideas. And I'm not really going to talk in standard reinforcement learning terminology for the bulk of the lecture. But towards the end of the lecture, I will just bring up the connections with standard reinforcement learning, and I'm going to give you a dictionary to translate between the words and terminology I'm using here and the sort of standard ideas in reinforcement learning that you may have already encountered. So I'm just going to provide that so you have a sort of conceptual anchor at the end if you're already familiar with reinforcement learning ideas. And lastly, I'm going to talk about a particular kind of reinforcement learning training called reasoning training. I'm going to introduce the idea of language models as reasoners, and I'm going to talk about how you can train them to reason better. All right, let's get stuck in. So let's do a brief comparison of the difference between supervised learning and reinforcement learning, and then later we'll see how this plays out in the maths behind the method we're going to look at. So in supervised learning, you have demonstrations of the desired behavior. So there's some behavior you want the language model to exhibit, and you have demonstrations of that behavior, and you train the language model to mimic those demonstrations of the behavior, right? Whereas in reinforcement learning, the model itself is going to generate many possible behaviors for you. So you're going to sample from the model to generate possible behaviors, and then you're going to choose those behaviors that are best. So you're going to somehow select between these different behaviors and then reinforce into the model those behaviors that are best, that are optimal. So in supervised learning, you're training the model to imitate the demonstrations. And so in the context of language models, we sometimes call this imitation learning. Whereas in reinforcement learning, you're reinforcing into the model the behaviors that lead to the highest reward, right? So the model generates its behaviors, you select among them which you think are best, and then you reinforce those behaviors into the model, right? So in order to select between different behaviors, so you can choose which ones you want to ingrain into the model, which ones you want to reinforce into the model, you need to have what's called a reward function. So in reinforcement learning, the reward function is basically a way of quantifying how good is a completion for a given prompt. So just to remind you of this notation that we introduced in the last lecture, by X here, I'm going to be denoting the prompt, right? So that's the question that I'm asking the language model, or the instruction I'm giving it, right? So that sort of description of the task I want the model to complete, that's what I'm denoting by the X. And then Y is the completion. So it's the output of the language model that sort of is supposed to be a solution to the task or a response to the instruction being given, right? So these X, Y pairs are prompt completion pairs, and what I need is a reward function that is quantifying how good the completion Y is for the prompt X. So how well do I do at the task being assigned? And the reward function, its role within reinforcement learning is to steer the model towards behaviors that result in a higher reward, right? So again, it's a selection mechanism. It's going to place selection pressure on these completions, and it's going to allow us to move the model towards completions that obtain a higher reward, right? So how do we create these reward functions that we're going to use for training the model? Well, for many kinds of behaviors that we want the model to exhibit, it's very hard to write down a reward function that accurately captures the properties that we want the completions to have. So if I want my language model to be a helpful, harmless assistant, right, helpful, harmless, and honest, how am I going to write down a function or code up a function that can compute, was this completion helpful, harmless, and honest given this prompt? Right? Well, actually coding a function to do that is basically impossible. So we can't write down some sort of mathematical expression that encodes how helpful, harmless, or honest it is. And so instead what we do is we train a neural network to recognize and assign high reward to behaviors that exhibit the properties that we want. So to completions that are helpful, that perform the task being asked, and harmless and honest. And sorry, I should say next lecture. So next lecture, we're going to cover this in a lot more detail. So it's all going to be about how do you train a neural network to recognize good completions over bad completions and assign those a high reward. So we've seen that there's one species of reward function that are called reward models. So that's what we've got here. We train what's called a reward model to model the rewards of the problem, to assign high rewards to those completions that are good. Another method that we can use is to have a programmatic reward function, so or a rule-based reward function. So reward models are neural networks trained to output reward, and this reward is just a quantification of how good is this completion, right? Whereas a rule-based reward function is some sort of programmatic check. So to give you a situation in which it would be appropriate to use something like a rule-based reward function, suppose I'm trying to train my LLM to act as a coding assistant. So I want it to be given tasks by the user or the client who's paying to use the LLM, and then on the basis of that, write code that satisfies the specifications given by the client. And so it might be that the way I do this is I have a number of checks. So I have tests that the function that I've asked the coding agent to implement is supposed to pass. I have my data set of checks. And then my rule-based reward function is going to be, I'm going to take the code that the language model outputs, I'm going to run it in my tests, and then it'll get reward depending on how many of these tests pass and how many fail. Or maybe I just demand that it's going to get a reward of +1 if all of them pass and 0 if any of them fail, because it clearly hasn't done it properly. So that's a situation in which I would use something like a programmatic check to evaluate output quality. And in general, these rule-based reward functions are very helpful in situations where it's very easy to algorithmically or programmatically verify whether an output does a good job, but maybe harder to generate that output itself. So also appropriate for something like maths tasks, where it's often easy to check that the answer that's being derived. If you ask, find x, it's often easy to check whether x is correct because you can just plug it back into the equation. If the equation's satisfied, you did the right thing. And so you can use something like a rule-based reward function for something like maths or programming or multiple choice question answering. And you use a reward model for tasks that are like be a helpful, harmless assistant, where you can't really specify in either mathematics or code what it means to be helpful or harmless. And you instead need to train a neural network to select the helpful and harmless behavior. And next week, we're going to cover that in a lot more, or next lecture, we're going to cover that in a lot more detail. But here are two species of reward functions that are often used for these kinds of training. Briefly pause now. Any questions? Cool, great. The last thing we need to introduce is this idea of regularization. So in general, in machine learning, regularization is when we add some sort of auxiliary objective or auxiliary loss to the thing we're trying to optimize, which encourages the solution we learn to have nice properties. That's the general concept of regularization. And here, we're going to use it to avoid adversarial examples for our reward function. So in particular, our reward model. So the reward model, remember, is a neural network that's going to take in these prompt completion pairs and spit out a reward. Now, you're probably familiar with the fact that neural networks are typically subject to adversarial examples. So it's usually possible to find very unnatural pathological stimuli that drive the neural network towards extreme values or very unnatural values that aren't what you would want the network to output. And so because our reward function is a neural network, there's a risk that if we basically ask the model to generate completions that have a very high reward, that it will just learn to generate completions that are like extremely pathological. So aren't in natural language at all, exhibit like weird tokens that barely ever come up, aren't grammatical, but that when fed into the reward model, drive the reward model to give an extremely high output, right? So there's a risk that if we just train on the reward model, we're going to get these adversarial examples coming up naturally. So the adversarial examples are sort of gibberish completions that the reward model thinks have a very high reward because it's a neural network and it's subject to these adversarial examples. So what we need to do is we need to put some sort of regularization in place that's going to demand that the completions that the RL model learns to output, the completions that it learns to output for these prompts are sort of natural and normal and aren't super weird, right? So we need to make sure it doesn't learn these kinds of gibberish text or nonsense. So how do we do this? Well, what we're going to do is that if something is very if something's nonsense, if something's gibberish, then it's going to probably have a very low probability under the SFT model, right? So the SFT model that we trained in the previous step of the pipeline, if the completions aren't grammatical, if they contain very strange tokens that barely ever occur, then it probably has a very, very low probability under the supervised fine-tuning model. And so accordingly, we're going to penalize the model for generating completions that are very unlikely under the SFT model. And so this is the sort of effective reward that we're going to use. So I'm going to use this terminology, effective reward. And let's break it down. Well, first of all, we have just the reward model or my reward function that's just quantifying how good it is. And this is either a neural network or a programmatic rule-based reward function. And then on this, the second half of it, this is my regularization term. And this is KL regularization is what I'm using here. And so tau here is quantifying regularization strength. If I move tau very, very large, I'm regularizing very, very severely. So I'm saying that I want you to penalize low probability completions very, very highly. And then this is the actual regularization term. So to break this down here, suppose that the probability of a completion is very, very low under the supervised fine-tuning model, right? So P SFT, y given x, very, very small. Well then, 1 over that is going to be very, very large, and log of that will also be quite large, and then I'm administering a large penalty for generating that completion, right? So the effect that this has is it warps the reward landscape in such a way that if you have a very low probability completion, a very low probability under the SFT model, and you generate it, then you're going to get a severe penalty, right? And we can see that this penalty gets worse the higher probability you assign to that completion. So P theta here is the language model I'm training, right? That's the model that's undergoing the RL training. And if y is very, very probable under the language model I'm training, so under the RL model, so P theta, but very improbable under the SFT, this ratio is going to be very large and the penalty is going to be very large, right? Any questions? Fantastic, right? So this is a regularization term, and it encourages me not to generate completions that are very improbable under the SFT model, which is going to avoid my adversarial examples. Okay, so this then is the reinforcement learning objective. So this is the thing that I'm going to try to optimize. So let's break it down. So J theta, J is what I'm going to use to denote objectives. So this is the thing I'm trying to optimize. Theta are the parameters of my network. So theta are all the parameters. This is a function of the parameters of the network. I'm going to try to optimize it. And then what is this function? Well, it's an expectation of that composite reward, the effective reward that I saw on the previous slide. So I'm trying to maximize the reward assigned to prompt completion pairs minus this penalty term that I have here, this regularization penalty. When I'm sampling, and then we'll see on the far side how I'm doing the sampling, I'm going to sample prompts from some prompt distribution, rho of x. So rho of x is a distribution of prompts. That's my data set of prompts that I've got. I'm going to sample prompts from that. And then y sampled from p theta y given x means I'm going to take my current language model, the current parameters of the language model, and I'm going to auto-aggressively sample from the language model given that prompt. And that's how I'm going to get my y's, right? So I'm trying to maximize the reward for prompt completion pairs minus a distance penalty from the SFT model, so stay close to the SFT model, while I'm sampling prompts from some data set of prompts that I've got, and I'm sampling my completions auto-aggressively from the model with parameters theta. Any questions about this? Yeah.
What does tau vary over? What's the typical tau size?
Oh, so typical values for tau are something like 0.05. That's a normal value to see for this, but it matters a lot what the scale of your reward model is, right? So if your reward model varies between, say, 0 and 100, you're going to have a different value for tau than if it varies over 0 to 10. But typically the sort of order of magnitude for these R's is like about 1, and then tau is about 0.05. That's sort of representative. There are some situations in which you want to vary this. This is a hyperparameter that you can change to get different model behaviors. Yeah. Great, other questions?
Do you sample uniformly from the prompts, or like sometimes more important?
Typically you sample uniformly from the prompts. Yeah, that's usually how you would do it. Anything else? Great, okay. So now I'm going to walk you through a sort of baby's first RL algorithm. So I'm going to talk you through an RL algorithm that will allow you to optimize this objective. It's very, very simple, and it's not really used in practice, this particular algorithm. There are variations of this that are used, and lots of extra tricks and sort of hacks that you can throw at this to improve it. But we're not really going to discuss them here because it gets very complicated very quickly. Instead, I want to provide you with a basic intuition for how these methods tend to work, what the underlying logic of them is, and hopefully this will give you a framework for understanding other methods that you might encounter, such as the frontier methods that are actually used to train these models. So this reinforces what we call a policy gradient method, which just effectively means that we're just going to iteratively update the parameters of the policy, which in our case is just the language model that's generating these completions. Yeah, so a brief note, there's many, many, many algorithms to try to optimize the reinforcement learning objective, right? Reinforce is just one of these algorithms. And the typical one that's used for RLHF is proximal policy optimization and various variations on it. One very popular one at the moment is group relative policy optimization, or GRPO, which makes some improvements over PPO. And reinforces, again, it covers a lot of the key ideas that PPO is going to build on. Okay, so let's have a look again. This is our reinforcement learning objective. Just briefly going to show this equation from last time, just to remind you all of how this works. So I'm going to exclusively be talking about log probabilities of completions given prompts. So log p theta y given x. Just wanted to remind you how you compute this. So the way you compute the log probability of a completion given a prompt is you sum over the log probabilities of each next token in the completion given the prompt and the previous tokens in the completion, right? And that's just what we saw last time, so that's how you actually compute these things. Just if you wanted to go away and implement this, how do you actually compute these log probabilities here? And it's just by summing over log probabilities of individual tokens. Okay, so the first thing I'm going to do is just replace this expectation with a sum over x and y, weighted by the distribution over x and the distribution over y given x, right? So nothing's going on here. I'm just rewriting this expectation in terms of the sum, right? Any questions at this point? Okay. So this is what I've got. I've got the thing in terms of the expectation. I've got the thing in terms of the weightings by the measure over probabilities and the measure over completions given given prompts. And then very simply, I'm just going to take the gradient of this thing, right? And so I get two terms coming out by the product rule. So one term is going to come from the p theta at the end, and that's my top term. And all I'm going to do is just take the gradient with respect to those model parameters, so the gradient with respect to theta of p theta y given x. And I have another term, which is going to come from the gradient of this minus tau log ratio here, and that's just going to look like this. Any questions at this point? Yeah. So I've got two terms coming from the two occurrences of p theta y given x. All right. Let's do some simplification. So this thing here, well, I can simplify by cancelling off the p theta that comes at the end and the p theta that comes from taking the gradient of the log, so the fact I get a 1 over p theta from the gradient of the log. And then I can rewrite like this. I'm also going to do one other trick, which is this grad theta p theta. I'm going to sort of do the inverse of this trick here, where the grad theta p theta can be written as grad theta log p theta times p theta. And that's what's happening here. I've got p theta grad log p theta, right? And then if I expand that out, that's just p theta grad theta p theta over p theta, cancel, and I get that there, right? So just the same trick applied one way forward and one way in reverse. Okay? Any questions? All right. So this is what we're left with here. Let's do a bit more simplification. So I'm just going to focus on the second term here. What I'm going to do first is I'm going to pull the gradient out of the sum, right? I can just freely exchange these. It's over a finite set. Everything's fine. I'm just freely exchange the gradient and the sum over y, right? And then I'm going to notice that sum over y, p theta y given x, this is just 1, always, right? I'm just summing over all possible completions, probability of that completion, right? And that must be 1, right? Sum over all outcomes, the probability of the outcome, that's 1. And then I'm doing gradient with respect to theta of 1, which is 0. So we see that the second term here just vanishes and I can ignore it. Any questions? This is a very nice little simplification. We can just get rid of that second term. So we're left with this. We've got rid of that second term. And now all that's left to do is just some neatening up, really, just smarten this up. So first of all, this thing here, which is the sort of composite reward, so it's the actual reward that I'm getting from my reward model or my rule-based reward function, RxY, and then minus the regularization term. And I'm just going to call this the effective reward, right? And this is just notation, right? It's just to simplify things later on. And I've kept in that it's a function of theta because it depends on the parameters of the model via the occurrence of p theta up there in the logarithm. Right? So this is my effective reward. And then I can just write it like this. Isn't that much cleaner and nicer to look at? And then the final thing I'm going to do is I'm going to note that here I have a sum over xy of rho x, p theta y given x. So this is just an expectation, right? I can just rewrite this as an expectation in the same way as before. Right? Great. And so this is an expression for the gradient of my reinforcement learning objective, and this is what we call the policy gradient. Hence why we call this a policy gradient method, because I'm conceptualizing my generation of completions as a policy for generating completions, and this is the gradient of the objective with respect to the parameters of that policy. Right, so this is the thing we've got. How do we turn this into an actual practical learning algorithm? Well, what I'm going to do is I'm going to sample a mini batch of prompts from my data set. So I have got a big data set of prompts. I'm going to sample from that data set of prompts k times, so capital K times, and get a bunch of prompts. And then I want to compute this expectation here. I'm going to estimate it by sampling one completion for each one of those prompts. And then I can replace the expectation with an empirical average over those prompt completion pairs. Right? So all I'm doing here is using a Monte Carlo estimate for this gradient. So I'm replacing the actual expectation with an empirical average formed by sampling from those prompt completion pairs according to that measure that we have in the expectation. Any questions? Great, so this is reinforce. This is how you do the reinforce algorithm, right? You sample a bunch of prompts, you sample completions according to current models, and then you compute this gradient expression here. You perform one update of your gradient steps, then you sample new prompts, sample new completions, form this thing here, do one gradient step, new prompts, new completions, sample, form that expression, update, you keep going like that. Does that make sense? This is the reinforce algorithm, and it lets you gradually increase or move your parameters in the direction of increasing value of the reinforcement learning objectives. All right? So let's just do a brief comparison with supervised learning. So this is the gradient that we form when we're doing reinforcement learning, right? How does this compare to the gradient we form when we're doing supervised learning? When we're doing supervised learning, we're just doing gradient ascent on the log probabilities of the completions. So there's two key differences here between how reinforcement learning and supervised learning is going to work. So firstly, in reinforcement learning, you're going to weight your samples according to the effective reward that they get. So you're going to see that samples that achieve a very high effective reward will get a high weight. So we'll get a weight of r theta xy that's going to increase how much I care about fitting to them. And in the case that the effective reward is negative, I'm actually going to be trying to unfit from them. I'm going to try and decrease the probability of that completion. So in reinforcement learning, I have these weights that occur in front of my log probabilities that are going to encourage me to fit more to those completions that had a very high reward. The other key difference is where my completions come from. So in the case of reinforcement learning, at each step, at each update step that I do, I'm going to resample a bunch of completions from my current policy, right? So in my current policy, I resample completions from that policy, and I fit to the best of those. So I fit to the ones of those that have the highest reward. Whereas for supervised learning, my completions come from some demonstrator policy, right? So I have my demonstrators, which practically speaking are people that I hire to write completions, generating those completions, and then that's where I get my completions from. So this gives you some intuition for the key differences between these methods. Any questions? I went through a lot there. Okay, great. I'm briefly going to talk about another very, very different approach to optimizing the reinforcement learning objective, which is called best of n sampling. In typical reinforcement learning, what you're doing is you're expending additional training compute. So you have some compute budget for training your model, and you're going to expend more training compute to increase the quality of the samples drawn from your model. So it's a training time compute method. Best of n sampling is another method which expends inference time compute, which means that you have the model, now you want to use it, right? You're not going to update the model at all, you're trying to use the model for some purpose, and you're going to be spending inference time compute, so time at the point of use, to increase the sample quality. So how does best of n sampling work? Well, you probably can guess it from the title. I'm going to have a prompt that I come in. This is the one that I want to do very good at, right? And then I'm just going to sample n times from my model, right? So I've got my model, and then I'm going to feed in that prompt and sample n completions from the model to that prompt. And then I'm just going to return whatever completion maximizes the reward. So whatever completion ends up with the maximum reward. Does this make sense? This is known as best of n sampling, and the cost of doing it grows linearly in the value of n, right? So if I double n, I'm sampling twice as many completions. It costs me twice as much compute at inference time. And typically, this increases the reward that you're going to get for the highest value of or the completion you actually return, but at the cost of increased compute expenditure, right? I'm going to briefly talk about, to set the next lecture up, a method called expert iteration, which is sort of a training time version of best of n sampling. I'll explain why this is helpful in a minute. So this is an alternative training time method that basically utilizes best of n sampling. And the method is very simple. You sample a bunch of prompts. For each one of those prompts, you sample n completions, and you select the best completion from those responses. So you do best of n sampling to get high reward completions for each prompt you have in your data set. And then you're just very simply going to do supervised fine-tuning to fit the model to the best of the end completion, right? To the best completion from that batch of n. And so what you're doing is you're getting the model to generate a bunch of completions, and you're fitting it to the best one of those completions that it generated. And you just repeat this. So you do your supervised fine-tuning loop, and then you can just go again, right? And this is called expert iteration. So one reason this is like super helpful is because suppose that you want to do reinforcement learning on GPT 4.0, right? Which is a closed source model that's behind OpenAI's API. And at the moment, OpenAI only lets you supervise fine-tune the model. So there's no option to reinforcement learn on the model, right? In this case, you can just apply expert iteration to do reinforcement learning only through a supervised fine-tuning API. So this is a very helpful thing that you can do with expert iteration, which is why it's very useful for researchers who are looking to work on these models, despite not having access to the underlying model weights. So you can still do a cheap form of reinforcement learning through something like expert iteration. Any questions about either best of n sampling or expert iteration? Pretty simple ideas. Fantastic. Okay. So now we're going to change pace for a moment and talk about standard reinforcement learning. I'm going to give you a dictionary for converting between the ideas that we've encountered so far about prompts and completions and various concepts that come up in standard RL. So what does standard RL deal with? Well, standard RL is focused on sequential decision making. So the basic concept is I have some policy of some kind, and I have an environment, and the policy repeatedly makes decisions within that environment. And the decisions that it makes give it some reward and move the environment onwards in some way. So cause the environment to change where it is and how it goes. So you can think about something like a game of chess. You're sequentially making decisions about what piece you want to move, and each decision you make changes the environment in some way and brings you closer to an end state of either being in checkmate or doing checkmate, which are either desirable or undesirable. And so you have a sequence of decisions to make to try to achieve some desirable end state. So a policy makes a sequence of decisions within this environment, and following each decision, the policy receives some reward, telling it, which basically quantifies how good was that decision. And what you're trying to do is to maximize the cumulative reward over the entire interaction. So you're not just trying to pick whatever local action achieves the highest reward. You're trying to pick which sequence of actions will eventually lead to the highest cumulative reward over the entire sequence, right? So just like in chess, you're not locally just trying to capture as much material as you can at every single step. Instead, you're trying to choose a sequence of steps which together will allow you to achieve checkmate, right? Because that's the thing that you care about in the end. So this is a little diagram that's typically used to illustrate how this reinforcement learning setup goes. You have an environment and a policy, and the environment is going to send a state S into the policy. right? And then on the basis of that state S that's fed into the policy is going to choose an action A, right? So feed a state S into the policy chooses an action A and sends it back to the environment saying, this is what I want to do. And then in response to that, in response to the action taken, the environment is going to transition into a new state. So this is the S prime here, new state, which will then get fed back into the policy, completing the loop and allowing us to go again. And it's also going to emit a reward. And then it's the sum of these rewards over the entire what we call trajectory that we care about maximizing. And this process will loop over and over again until eventually we hit what's called a terminal state, where the environment is sort of, that the interaction is finished, and then we reset the chess game, and then we go again, right? So this is standard reinforcement learning. Any questions? Okay, so how do we convert between the ideas of standard reinforcement learning we just considered and all this stuff I was talking about at the start of lecture? So the way we do this is we see text generation as sequential decision making. So when you generate a completion, what you're doing is you're repeatedly generating single tokens. And each one of those tokens can be seen as a decision. What am I going to say immediately next, right? And what I want to do is not just say immediately the tokens that I think are best. I want to produce a sequence of tokens, a string of tokens, which together end up generating a high value, a high reward completion, right? So which token to generate at each time point is a decision, and that's how we see text generation as sequential decision making. Any questions about this? Right, so how do you map these concepts? So what's the state in language modeling reinforcement learning? Well, the state is just the current prompt that I have and the partial completion. So whatever tokens I've presently generated, that's the state. So that's fed into the model. The model's fed in all the tokens in the prompt and the tokens it's currently generated. It's fed into the model. On the basis of that, the model has a probability distribution over next tokens, and so the action is which token is generated next. Right? And the model outputs a probability distribution over next tokens, and then samples from this to choose an action of what token to generate next. Transitions just amount to appending that next token to the current partial completion, right? Extending the completion by one more token. Right? The terminal state is when the completion ends. So the model keeps generating tokens. Eventually it generates a special token called an end of sequence token. Or it hits a maximum length, at which case we like truncate and we stop going there. Usually penalize it for not having generated an end of sequence token within some window that we have. So the model generates a special token called an end of sequence token, and when you append that to the completion, you're done. That's the terminal state. There's no more interaction. You're done then, right? And the rewards, well, in language modeling RL, there's no rewards for any transition, except when the EOS token is produced. That's where you get the effective reward, right? Okay. Any questions about any of these mappings between these? If you've encountered standard RL, this will give you a way of understanding what we covered today in terms of those concepts. Okay. So the last thing we're going to cover today, just briefly at the end, is what we call reasoning training. So the idea of using language models as reasoning systems, well, one of the papers that popularizes this is chain of thought prompting elicits reasoning in large language models. So what is chain of thought prompting? Well, here we have an illustration of chain of thought prompting, which is they're trying to use in-context learning. So to remind you, in-context learning is where you demonstrate to the model the behavior that you want it to exhibit, and then on the basis of that, it then exhibits that behavior on the next examples that you give it, right? So this is in-context learning. In the context, you give it examples of what it's supposed to do, and then it continues from there. And what they're doing here is they're using chain of thought prompting within the context. They're doing in-context learning here. So on the left, we have standard prompting, where you have some question that's sort of, it's a natural language maths question. So Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? And the model guesses, and it's wrong. Oh, sorry, no, it's right here. And then there's another question and then the model is asked to generate the output, and it gets it wrong. Whereas on the other side, for the chain of thought prompting, within the context, they demonstrate the model, or they demonstrate reasoning through the problem that's been given. So the reasoning goes, Roger starts with 5 balls, 2 cans of 3 tennis balls is 6 tennis balls, 5 plus 6 is 11, the answer is 11. And then the model uses in-context learning to exhibit the same step-by-step reasoning process when it has to generate its output. And so it says the cafeteria had 23 apples originally. They used 20 to make lunch, so they had 23 minus 20 equals 3. They brought 6 more apples, so they have 3 plus 6 equals 9, right? So it breaks it down into these step-by-step operations, completes each one of the step-by-step operations, and then gives an answer, right? And so this sequence of reasoning steps is what we call chain of thought, right? In analogy to how when a person's solving a difficult problem, they often break the problem down into a sequence of steps, go through each one of those steps, and provided each one of the steps is right, you've reached the right answer at the end. So this is called chain of thought prompting. Any questions about this? Okay. So briefly, let's discuss why does this work. So it does. It's a very powerful technique. It's a very good way of getting extra juice out of your language model. And basically, it's for the same reason that people think out loud or externalize their cognition in some way, right? So when you go to solve a difficult maths problem or solve some sort of programming problem, you don't do it all in your head, typically, and then just write down the answer at the end. Instead, you probably pick up a pen and paper, and you work through line by line a sequence of steps that's going to get you that right answer, right? And the reason is because each one of those steps is simpler than just getting the right answer at the end, right? And when you're thinking to yourself about like what could happen, reasoning through a sequence of operations, each one of those reasoning steps is typically easier to perform than the composite of just getting the right answer immediately at the end. So what COT is doing is it's allowing the model to sort of externalize cognition in some way, where the model can write down, and in its completion, the various single steps that it's going to put together to form the right answer, and then it just needs to put these together, which is typically much easier than just getting the right answer at the end. So if asked to produce an answer immediately without reasoning, the response quality of the model is fundamentally bottlenecked by how much reasoning can be done in a single forward pass to the model, right? If I demand that this is my question, and then the next token I demand that the model gives me the answer, I do answer, colon, then demand that the model immediately tells me what the answer is, then the amount of reasoning it can do is just bottlenecked by the forward pass of the model. The fact that it can only get this much. And if you're bottlenecked for each individual token you produce, you're bottlenecked by a single forward pass, then it makes sense to decompose the complicated problem into a sequence of easier prediction problems so that you can solve each one of those easier problems within a single forward pass and then just put them together at the end. So COT is another method we saw earlier about best of n sampling. It's another method of being able to trade in more inference time compute for improved performance, right? So if I'm generating a COT, then the amount of tokens my model produces goes up by potentially quite a lot. You know, the COT that's produced can be much, much longer than the answer that the model ends up arriving at, especially in something like a maths problem. And if the COT is much longer than the answer that's arrived at, then I'm basically expending a lot more inference time compute to get the model to generate all that text, right? Every token generated is extra compute, and that costs me something. So COT is another method whereby if I can train the model to exhibit COT, then I'm basically getting the model to do better at inference time by spending more inference time compute. Does this make sense? Okay. So this is an example of how you can train a model to do chain of thought reasoning. So this is incentivizing reasoning capabilities in LLMs via reinforcement learning. This is from 2025, so very, very recent. And essentially, they start the prompt with this text here. A conversation between a user and assistant. The user asks a question and the assistant solves it. The assistant first thinks about the reasoning process in the mind and then provides the user with the answer. The reasoning process and answer are enclosed within think tags and the answer within answer tags respectively. I.e. think reasoning process here, end think, answer, answer here, end answer. And then the user goes prompt, and then it goes assistant, and lets the model generate from there, right? And then you train the model to use this formatting, so to use these think, end think, and answer, end answer tags, and then also to generate thinking within the think tags that allows it to give a good answer within the answer tags, right? So that's what you're training it to do here. So how does reasoning training work? Well, now the model is going to output a reasoning trace, or a COT. There's another word for a COT is a reasoning trace, and I'm going to denote that with a Z, right? And so you're sampling the reasoning trace, Z, and the answer Y, right, from the model. So you feed in the prompt, and then you're generating reasoning trace, and then the completion. And then, typically what you do is you evaluate the reasoning trace and the completion. So your composite reward for the two things the model's generating is going to be decomposed into just how good is the completion for the prompt that's fed in, and often also an auxiliary reward on something to do with how good the reasoning trace is. So sometimes this is left out completely. Sometimes you don't have anything on the reasoning trace, so you only care that the completion is appropriate for the prompt, right? But often you add something in that looks at the reasoning trace and rewards or penalizes that reasoning trace, and that can be things like, is it logically coherent? Is it consistent? Is it on track? Is it all in the same language? So in the paper that we're looking at here, this DeepSeek paper, they found that the model often switches languages midway through the reasoning trace, and this is undesirable for a number of reasons, so they penalize it for switching languages. They demand that you only think in one language at a time. Great. Any questions about this? Yeah.
Didn't OpenAI release a paper that says that you shouldn't train on reasoning trace?
Yes. So, for various reasons, you probably shouldn't train on reasoning traces. I think we're going to cover this in a lot more detail later on in the course. I'll briefly give you the quick gist of it, which is if you train reasoning traces to look nice, but you still reward bad behavior. So if these are sort of misaligned with one another, so the reasoning trace says, so this part says, make sure the reasoning trace looks nice. But this part says, but if you do something bad that we don't want, we're still going to give you a high reward for it. Then what the model learns to do is just generate reasoning traces that look nice and also bad behavior, right? So then this is called obfuscation. It obfuscates the underlying reasoning behind the bad behavior so that the reasoning trace looks nice, but the behavior is still exhibited. So you exhibit this obfuscation, and what this means is that the reasoning trace, so the Z, no longer provides useful information about what the model is going to do, because you just decoupled them. You're placing optimization pressures in different ways, and you end up decoupling the reasoning trace and the completion you end up at the end. So generally speaking, a bad idea, and I think we're going to discuss more of that later on in the course. Yeah.
And why do you just use a minimum instead of the plus between the two risks?
Yeah, in that case, you have the same incentives, right? If you replace this with a minimum here, you're just incentivizing the model to generate, again, completions that look nice, so have a high value of RxZ, and that do the bad thing RxY, right? So the problem is that in the situations we're talking about where you get the obfuscation, the model can obtain a high reward by doing some bad behavior that we don't want it to do. And this is called reward hacking. And again, we're going to talk about this later on in the course. So the model can output some Ys that obtain a very high value, but we don't want it to, right? And so what we're trying to do is we're going to say, well, we're just not going to let you think about doing the bad thing. We're going to penalize this reasoning trace if the reasoning trace exhibits you thinking about doing the bad thing. And what the model learns to do is it just does the bad thing to achieve a high value of this, but then doesn't appear to think about doing the bad thing, so it can get a high value of this. So using a minimum wouldn't help, or basically any combination of these that's reasonable will lead to the same incentive structure for the model, and the model will learn to obfuscate the bad thoughts rather than letting you see the bad thoughts, which is arguably a much more useful way of predicting what the model's going to do, monitoring it, and making sure it doesn't do things that you don't want it to do. Yeah. So you generate the prompt completion pairs, and then all the rest of the derivation is exactly the same, right? You just have this x, y now instead of your y. and all the rest of the derivations are the same, and the rest of the methodology is the same. Okay, end of the lecture. Let's briefly recap what we did today. So in RL, the model is generating completions, and those completions that generated the highest effective reward get trained into the model. So they get reinforced into the model. The model is encouraged to keep generating completions like that. Policy gradient methods, like reinforce, work by weighting samples according to effective rewards, and then encouraging samples that, or training in those samples that achieve a high weighting. Best event sampling is another inference time method that you can use to increase the qualities of samples drawn from the model. Lastly, we discussed chain of thought, which provides another method to improve model quality by spending more inference time compute, by getting it to generate a sequence of reasoning steps that you can condition on. And finally, models can be trained to produce better COT through reasoning training. So you can train in the ability to generate COT. Thank you very much.